the atom became obsolete in the early 20th century. Then Niels Bohr made a series of revolutionary proposals that allowed the model of the atom to cross into the land of quantum physics. Bohr proposed that an electron orbiting the nucleus of an atom is constrained to occupy certain definite orbits or energy levels. It does not normally emit radiation, not in the ground state or closest possible orbit, or in any excited states, as the further permissible orbits are called. Bohr explained how atoms emit radiation based on the energy level of an electron in each orbit, and used these values to predict all possible frequencies of radiation for a hydrogen atom. Bohr's predictions could be put to a practical test because detailed observations had been made of the frequencies emitted when hydrogen is bombarded with electrons in a discharge tube. In the late 19th century, a Swiss schoolteacher, Johann Balmer, had observed the spectral lines in the visible region of the spectrum of excited hydrogen gas. What's more, he had developed a formula that correctly predicted these lines. In 1908, the German physicist Paschen detected hydrogen emission lines in the infrared region of the spectrum of excited hydrogen gas. In 1914, Theodor Lyman identified the ultraviolet region of the spectrum. Bohr's predictions matched all these observations to a high degree of accuracy. Still, Balmer had already produced a workable formula for predicting lines, but no one really knew why it worked. What made Bohr's mathematics so special was that they were based on a possible structure of the atom. Imagine that a collection of hydrogen atoms could be gathered, all in the ground state. Further, imagine these atoms could be bombarded by precisely tuning the energy of every free electron in a spark tube. At the lowest energy levels, the hydrogen would emit no radiation. But at a certain level, radiation would begin. What level? According to Bohr, the level of the next possible orbit. When this magic number is reached, hydrogen would emit one and only one frequency of ultraviolet light. But why just one frequency? Free electrons would have just enough energy to bump the orbiting electrons up to the first excited state, n equals 2. This action would cause no radiation to be emitted, but eventually the electron would spontaneously drop back to the ground state. In so doing, it would radiate all the energy it had gained, the difference between the energy levels of the two orbits, exactly 10.2 electron volts. Using Planck's constant, the wavelength of this photon can be calculated exactly. This frequency is in the ultraviolet region of the spectrum. Bohr proposed that each emission line in a hydrogen spectrum corresponds to the energy difference between two specific permissible orbits. The Balmer series is produced as electrons drop between orbit n equals 3 to n equals 2. N equals 4 to n equals 2. And so on. Infrared radiation in the Paschen series is produced by jumps to n equals 3. Ultraviolet radiation in the Lyman series is produced by jumps to n equals 1. Bohr had produced the first real explanation of a frequency spectrum. every line corresponding to the energy difference between two permissible orbits of an electron about the nucleus of an atom. Bohr's model of the atom cleared up another mystery of science, which had been of great practical value, but was completely unexplained. Early in the 19th century, the English scientist William Wollaston observed 7 dark lines in the spectrum of sunlight. A decade later, Fraunhofer resolved these initial 7 lines into many hundreds. In 1860, Kirchhoff found that when an intense light source is shone through a spectrometer to produce a spectrum, and then a sodium flame is interposed, some of Fraunhofer's dark lines are produced. Kirchhoff recognized that a substance capable of emitting a certain spectral line has a very strong absorptive power for the same line. Bohr's model suggests the reason. An electron can emit a particular frequency as it drops from one orbit to another. It can also absorb a photon of exactly the same frequency, which gives it the energy to jump in the opposite direction to a higher excited state. Long before Bohr's explanation, Kirchhoff's work had produced the technique of spectral analysis, which has enabled scientists to determine the composition not only of earthly chemical compounds, but substances beyond the Earth, including the sun and the stars as well. Here's how it works. An intense light source like the sun radiates in all directions. Only a portion of all radiated light, however, is directed toward an observer. If a sodium flame is placed in the path of the light, the sodium absorbs and then re-radiates only certain frequencies. This re-radiation likewise occurs in all directions, so that only a tiny portion of the absorbed frequency continues in its original direction. The result is a sharp decrease in the intensity of the light reaching the observer from that portion of the spectrum, and hence the appearance of dark lines in the spectrum. An imaginary sunbather whose skin was sensitive only to the absorbed wavelength would take a long time to acquire a tan. Fraunhofer's many dark lines are produced as atoms in the sun's atmosphere absorb and re-radiate particular frequencies. Bohr was able to use his model of the atom to predict the results of many scientific experiments. And yet there were problems. For example, his theory worked for hydrogen, but could not predict the behavior of other atoms. Nonetheless, Niels Bohr had made tremendous strides along the road to an understanding of atomic structure.